tell you to bring a jacket because I have no power over how hot or cold it is in here. All right, so we've just got 2 more sections of these this unit that we have to do. I am behind on getting everything planned out, so I'm gonna work on it during planning today, and I will have the weekly learning plan done by then. You're probably looking at a test towards the end of this week, Thursday or Friday. I've just got to look at the schedule and see, preferably Thursday, because Friday is a pep rally schedule and short schedule. So that my hope is to get it in by Friday, by Thursday, which I think we can do. All right, so our most basic rational function that you can deal with is just f of x equals 1 over x. Okay, so you'll see that there on your notes. And f of x here has a horizontal asymptote at your horizontal asymptote is this horizontal line right here. These dotted lines are not part of the graph. They're just there so you can see them. At y equals 0, which y equals 0 is the x-axis. Okay, and it also has a vertical asymptote at x equals 0, which is your y-axis. It's the opposite, yes. So vertical lines are going to be x equals a number, and horizontal lines are going to be y equals a number. So you might even want to write that down as a note there. Vertical lines are x equals a number, and horizontal lines are y equals a number. So if you get a question that asks you for vertical asymptote, it needs to be x equals a number for the line. If there's any options that are y equals, then those are wrong. You could throw them out automatically. Again, you won't see that today, but on the test that we'll have Thursday, you'll see some of those. Okay. Questions? All right, so looking at asymptotes is one thing we're going to do. I went through the standards for this class several times, and I am pretty sure that at this level in Math 3, we are only really expected to be able to find these from a graph. We do not necessarily have to know how to do it from the equation. I'm going to show you something about doing it from the equation because I think it makes it easier to see from the graph. But I think we will mostly be dealing with the graphs. However, they may give you the equation and you may have to type it into Desmos yourself for the graph. They may not give you the picture of the graph. It just depends. For this, we're supposed to give the equations of all asymptotes for the following functions. So again, there are ways of doing this from the equation. We don't have to be able to do those. That's at the next pre-calculus level that you have to know that. So we can just graph these. So if I go over here to f of x equals 3x minus 2 over x plus 1, x minus 2. All right. So we should be able to see whenever you have this sort of happening here where it goes down and it gets really steep and then it flips up here, there's probably a vertical asymptote there. And you can type in, if you're not sure, if you type in x equals -2. Oh, that's not it. Maybe x equals -1. That looks like the right place, right? So you would have, for this one, you would have, I'm just going to do VA for vertical asymptote. You would have a vertical asymptote at x equals -1. And then it looks like I have another one over here at probably 2. Let's type it in to see if that looks right. X equals 2. That looks like it is also a vertical asymptote. So x equals 2. And I believe that would be our only vertical asymptotes. What do you notice about our answers for this and the equation? It's those numbers that give me the zeros in the denominator. It's just the opposite sign, right? So that happens on these problems. That's something that you're going to see. So that denominator, even though we don't have to be able to do it from the equation, that can help us whenever we're seeing what we need to see from the graph. Now, horizontal asymptote is different. This is weird. Okay, no, never mind. I see why. Okay, I'm thinking of it from the equation, and I was thinking of. So, what we're looking at for horizontal asymptote is like if we zoom way out. What I want to know is like, does this go up forever, or does it kind of even out at a number? You might want to zoom out to kind of see what's happening here. So if I zoom out, does it look like I'm ever crossing this line right here? Nah. How about over here? Not really. And if I zoom out even further, it just starts to look like it is the line itself. So this appears to probably have a horizontal asymptote out on the ends at the x-axis, right? It does cross the x-axis here. That is okay. You can cross whatever the horizontal asymptote is. What you're looking at is what happens on the ends. If it gets really close to a line on the ends, then that's a horizontal asymptote. So this one would have a horizontal asymptote at the x-axis. What's the equation for the x-axis? It's y equals 0 for that. Because all of your horizontal lines are always y equals a number. Okay. Questions on that one? It's not always 0. There's definitely somewhere it's going to be something besides 0. But when in doubt, y equals 0 is your best guess, because it happens a lot. We're going to see it on the next problem as well. All right, let's go to the second one here. Let's type that in. We got 7. Ooh, that's not what I want to do. 7x over 2x minus 3 and x minus 1. I think that there's something different about this one. This one is different than I was expecting it to look, actually. Why is that like that? Okay, so if I'm looking for a vertical asymptote here, it looks like probably x equals 1 might be. This one's kind of weird, because usually there's something in between here. But it does look like that probably happens for my y equals 1 there. So, and notice here I've got x minus 1 here, so that makes sense to have a y equals, or not y equals, x equals 1. So I've got a vertical asymptote at x equals 1. There's going to be another one for this one. It's not very easy to see, because like if I zoom out here, it will eventually kind of look like it's just the asymptote for both of them. But if you zoom in, there's always going to be, like, those two lines are basically together. If I click here and the purple line, those two are basically together. You got this big gap over here for this one. So if I use what I know about the denominators, I also cannot have 2x minus 3 equal to 0, right? That would give me something undefined in the denominator. So if I do, not that, if I do 2x minus 3 equals 0, if I solve that, I'd move the 3 over, and it would be 2x equals 3, and I could divide by 2. So x would equal 3/2 or 1.5, whichever one you want to use there. Let's type that in over here and see what that looks like. X equals 1.5. And if I sort of zoom in up here, go up here, that looks like it is also a vertical asymptote, right? So my other vertical asymptote would be at x equals 1.5 or at 3/2. So although we don't have to know how to do it from the equation, I think in particular on this one it helps to know how to do it from the equation because on the graph it's a little hard to see because those two are very close together. So you got two vertical asymptotes for this one. If I go back, horizontal asymptote, I'm thinking about like on the ends, what do I get closer and closer to? And it looks like that red graph gets closer and closer to the x-axis again, right? It's just getting closer and closer there. So the x-axis for a horizontal asymptote is y equals 0 also. Okay, and you can type those in as well, you know, on Desmos. That'll help you because you'll probably see these as multiple choice most of the time. Make that blue. Go back in, you can see that looks like a horizontal asymptote for that. We okay here? All right, let's keep going. All right, so there are two types of discontinuities that you are going to see on these problems. Rational functions are going to have either removable discontinuities, which are holes in the graph, or vertical asymptotes, which we just looked at. So like if I look at this graph over here and label these things here, right here at this point, this is where I have the hole in the graph. So a hole in the graph is just one place where it's undefined. If you graph it on Desmos, you can't see it until you drag the cursor there and it turns to a hole. I showed you this on some of those problems where we had those excluded values. These are basically some of your excluded values. And then vertical asymptote for this one, it would be this line right here. That would be your vertical asymptote. Okay, so from the equation, there's a way to tell where you will have holes and where you will have vertical asymptotes. For holes, you will have a 0 in, oh wait, I may have put this on another slide. Hold on. Let me skip ahead and see. Yes, okay, it's on the next slide. I don't need to write that right there. So let's look at this slide. Okay, discontinuities happen at any value that will give you a 0 in the denominator. So for example, if I'm looking at this equation right here, I would look at the denominator right here, and anything that would give me zeros in the denominator would cause a discontinuity. So x equals -2 and x equals +3. These would be discontinuities. And a discontinuity is where that we either have a hole in the graph or vertical asymptote. Like if you're trying to trace the graph, you'd have to pick up your pencil. Now, if I graph this graph right here on Desmos, I just put it here for you, it looks like I have a vertical asymptote. It looks like that vertical asymptote is probably about right here at -2. Do I have another vertical asymptote? At x equals 3. Is there a vertical asymptote here? Right here would be 3. I do not have a vertical asymptote there, right? So, the way we can tell what's going to happen from the equation, vertical asymptotes occur at values that make only the denominator equal to 0. But removable discontinuities, or holes in the graph, occur at values that make both the numerator and the denominator equal to 0. So if we're looking at this x minus 3 right here, if I plug in 3, that would give me 0, right? But it's also up here in the top as well. So if I plugged in 3, I'd get 0 in the top and the bottom. So if we have a factor that's in the top and the bottom, it means there's a hole in the graph. I specifically did this on purpose. This doesn't show the hole, because when you graph this on Desmos, the hole is not going to show up unless you take your cursor and drag it exactly to that point. Okay? So there would be a hole in the graph right here, an open circle where it's undefined at that point. But you can't see them from the graph when you look up on Desmos unless you drag your cursor there. The vertical asymptote should be more obvious. You can see right here at -2, you only have a 0 in the denominator. The top would not be 0. So if a factor is top and bottom, that's a hole. If it's just in the bottom, that is a vertical asymptote. What about at 7 for this? Is there a discontinuity at 7? 7 gives you a 0 in the top. Is it okay to have zeros in the top of a fraction? Like 0 divided by 5? That's fine. If you somebody type 0 divided by 5 into Desmos or into your calculator, what is 0 divided by 5? It's just 0, right? You're not going to, now 5 divided by 0, zeros in the bottom are not okay. But zeros in the top are okay. So that 7 doesn't do anything right there. It is your, I guess it's your x-intercept right there, if you want to think about that. All right, we okay here? All right. So for each of these, we're supposed to tell the discontinuities and describe the type. So I'm going to graph a couple of these, but not all of them. Okay? So if I put this over here and I graph this first one, I've got f of x equals 1 over 2x minus 5. All right. That looks like to me it has a vertical asymptote. Where does it look like that is at? What do you guys think? All right, so if I do x equals 2, is that the vertical asymptote? No, because it touches it. So that's not it. 2.5. Oh, that looks better, right? That looks right. And I can know that that's correct because vertical asymptotes happen when the denominator is 0, right? So if I do 2x minus 5 equals 0, if I add 5, 2x equals 5, I would divide by 2, x equals 2.5. So that is a vertical asymptote. I'm going to use VA for vertical asymptote. Does this have any holes in the graph? It does not, because there's nothing else that would make that denominator 0. It's the only thing. All right, let's look at example 4. Let's try to do this before we graph it, and then we'll confirm it with our graph from Desmos. So I want to look at the denominator right here, 5x times x minus 4. I want to think about what would make that 0. What values would make that denominator 0? X equals 4. What else? There's one more. Not 6. Not -1. 2? No, not 2. We're looking at, so the 4 comes from this part right here, right? This part, the 5x, also it cannot be 0, right? So if I have 5x equals 0, I just divide both sides by 5 there. X. What is 0 divided by 5? 0. So x cannot equal 0 either. So it's like your excluded values that we were doing for the other problems. This time we're just talking about what it looks like on the graph. So if I plug in 4, that is only going to give me a 0 in the bottom. Okay? If you only have a 0 in the bottom, that is a vertical asymptote. What about if I plug in 0? Would that give me a 0? It will give me a 0 here. What about if I plug in 0 in the top? What will I get? Also 0, right? So that means that should be a hole in the graph. Okay? Let's graph it and confirm that we have done this correctly. So if I graph f of x equals 2x over 5x times x minus 4. And I think there's a vertical asymptote at x equals 4, so I put that there. Oh yeah, that definitely looks like my vertical asymptote. Now at x equals 0, I don't see anything right there. X equals 0 would be right here. But if I go and put my cursor there, you can see it's an open circle, it's undefined. Right? So holes don't show up whenever you graph them unless you go straight to that point. And this does have a hole in the graph there, so we've done that correctly. Yes. It can just go here. It's fine. All right. So, let's do the next one. Let's graph it. X minus 4. I've got x squared minus 3x minus 4. All right. That looks like it has a vertical asymptote. Where do you guys think the vertical asymptote is? At negative what? 1. All right, let's try x equals negative 1. Oh, I think that's right. That looks good. All right, so this one looks like it has a vertical asymptote at x equals negative 1. But like, if I'm looking for a hole in the graph, let's see if we find one. Not seeing a hole, but probably not going to be able to see the hole from the graph. So that's why I also want you to know how to do it with the equation over here. Because definitely that x equals negative 1, I really can't see what's happening there, right? Like I don't know that. So what if I factored this? So the top would stay the same. If I factor the bottom, I would have an x and an x, and I would need a plus 1 right here and a minus 4 right here, right, if I factor that. So you can see right here, you've got that x plus 1, and you had a vertical asymptote at x equals negative 1. Is there another number that would give you a 0 in the denominator? 4, right? So at x equals 4, I'll get a 0 in the denominator, but it'll also make the top 0 as well, right? So if I go to 4 on this graph, so x equals 4 right here, if I go to 4 on this graph, if I get right there on 4, I have a hole in the graph. But it's really hard to find that just by like scanning for it. So if you know how to do it with the equation, it helps a lot more. So you have a hole in the graph, oops, at 4. So you got a vertical asymptote at negative 1 and a hole at 4. Yes, it will probably be multiple choice, or it will have like a vertical asymptote here, hole here, and you would have to type that in. So, or maybe a matching or something. So, so yes, but it'll be kind of limited what you have to do with that. On Thursday? What's that one for? Okay. I'll have you guys take it Friday, whenever you're back. Okay. All right. So it's just you three.
Yeah.
No more. All right. Let's see. This last one here. Okay. Oh, does that have a vertical asymptote at all? No. So I bet there's a hole, though, because this has a denominator, right? So where do you think the hole might be? All right, so I think the hole is probably at 3, because 3 would make that denominator 0, and there's definitely not a vertical asymptote there. So if I go to 3, oh yeah, there's a hole right there in the graph. Now, if I wanted to, I could factor this top. It would be x minus 2, x minus 3 over x minus 3. So you can see how that x minus 3 is in top and bottom, so that's why you have a hole instead of just a vertical asymptote at that point. And this would be your only discontinuity for that one. Okay, questions? All right, let's look at the next one. All right, so we're just given a graph this time. We're supposed to find the x value for all discontinuities and describe the type of discontinuity at each value. I'm hoping this is what they might give you, more so even than the others. So, do you guys see a hole in the graph for that? What have we got? What is the x value at that hole? I think I heard somebody say it. What is it? -5. So we have a hole at x equals -5. And sometimes they're called removable discontinuities as well. So that is something I probably should be using, because I'm not sure what they might use on the actual exam. So you got a hole at -5. We have some vertical asymptotes. Looks like I've got one right here, and another one right here. So, Alvin, what's one of those vertical asymptotes? Okay, so x equals 3. What's the other one? -2. So x equals -2. I think that's mostly what they're going to ask you, which hopefully is not too bad. You guys okay on that? Being able to identify those? Because it said we need to be able to find it from the graph, not so much from the equation for that. All right. Okay, let's talk about domain and range a little bit. Actually, I want us to review just a little bit. Let's save domain and range for the beginning of class tomorrow so that we have some time to review for a few minutes to review for our quiz. So we're going to put a pause on these notes